Good morning, everyone. Today we're going to explore another powerful aspect of calculus, the rules of differentiation. In our previous lecture, we learned about the derivatives as a function and how it represents the instantaneous rate of change. We calculated derivatives using the limit definition, f prime of x equals to limit as h goes to 0 of f of x plus h minus f of x over h. While this definition is fundamental to understanding derivatives, applying it repeatedly would make calculus extremely tedious. Imagine having to use this limit process for every function you encounter. Fortunately, we have developed the rules that allow us to find derivatives quickly and efficiently. So we'll start with the constant rule. So let's start with the simplest possible function, a constant function f of x equals to c, where c is any real number. What does a graph of a function, of a constant function, looks like? It's a horizontal line with the slope of 0 at every point. So since the derivative represents the slope of the tangent line, we can intuitively see that the derivative of a constant function should be 0 everywhere. Let's verify this using the limit definition. So f prime of x is equal to limit as h goes to 0 of f of x plus h minus f of x over h is equal to limit as h goes to 0 of c minus c over h, right? So we don't have any x in this function, so that's why we'd have c minus c. So in this case, we have 0 over h, which gives us 0. This gives us our first differentiation rule, the constant rule. So d dx of c is equal to 0. If c is a real number, then d dx of c is equal to 0. This makes sense intuitively because the constant function doesn't change as x changes, so its rate of change is 0. Next, we'll consider power function of the form f of x equals to x to the nth power, where n is a non-negative integer. Let's look at some examples. So if f of x equals to x squared, its derivative would be equal to 2x. If f of x is equal to x cubed, its derivative is equal to 3x squared, and f of x equals to x to the fourth, its derivative is equal to 4x to the third power. Do you notice a pattern? In each case, we're taking the exponent of n and place it in front of x as the coefficient and then reducing the exponent by 1. So this gives us a power rule. So if n is a non-negative integer, then d dx of x to the n is equal to n x to the power of n minus 1. So we're taking this n, we put it in front, and then we reduce n the power by 1. Now let's look at a couple of examples just to have some practice. So first example, if we have a function x to the 9th power, we want to find its derivative. So what it's going to be, first of all, we need to bring this coefficient power to the front as the coefficient. So we'll have 9 and then x, and then we need to subtract 1 from the existing power. So we will have 9 times x to the 8th power. Now, another example. What is the derivative of 2 to the 8th power? Now, look at this carefully. You might want to say that it's 8 times 2 to the 7th power as before, but look at this carefully. 2 is not an x, it's not a variable. 2 to the 8 is a constant. In fact, if we raise it to the 2 to the 8th power, it's going to be 256. So we need to find essentially the derivative of a value 256. This is a constant, so the derivative of this function is going to be equal to 0. Constant multiple rule. What happens when we have a constant multiplied by a function? For example, how do we find the derivative of 5x squared or negative 3x to the fourth? So let's consider the general case of c times f of x, where c is a constant and f is a differentiable function. So using the limit definition, we have d dx of c times f of x is equal to limit as h approaches 0 of c times f of x plus h minus c times f of x over h. We can factor out this this c, and we will have limit as h approaches 0 of c times f of x plus h minus f of x divided by h. And now remember that we can factor out this c out front, and we will have c times limit as h goes to 0 of f of x plus h minus f of x divided by h. And look at this. This is exactly the definition of the derivative, so we can say that it is equal to c times f prime of x. So in other words, the derivative of a constant times a function equals to the constant times the derivative of the function. So now let's apply this rule and see a couple of examples. So what is the derivative of negative 7 over 8x to the 11th power? Okay, so negative 7 over 8 is going to be our c, or constant, so we can just write it as negative 7 over 8 times d dx of x to the 11th power, and we would have negative 7 over 8 times 11 times x to the 10th power, and from here we have negative 77 over 8 x to the 10th power. Okay, another example, d dx of 3 square root of 7, square root of x over 8. Okay, so now in this case, let's present the square root of x as the power. So we would have d dx of 3 over 8 times x to the power of 1 over 2. So now we can factor out this 3 over 8. And now we would have d dx of x to the power of 1 over 2. Now, let's look at this a bit more carefully. We need to bring down this 1 over 2 to the front and subtract 1 from the power. So we would have 3 times, or it's 3 over 8 times 1 over 2 times x to the power of 1 over 2 minus 1, which gives us 3 over 16 x to the power of negative 1 over 2. And if we simplify it, we get 3 over 16 square root of x in the denominator. So note that in this example, we're applying the power rule with the fractional exponent. So the power rule actually extends beyond integers, integer exponents to include all real number exponents, which we'll explore further in later sections. Next rule will be the sum rule. Many functions we encounter are sums of simpler functions. For example, polynomials are sums of power functions. How do we find the derivatives of a sum? So let's consider the sum of two differentiable functions f and g. So we would have d dx of f of x plus g of x. That is going to be limit as h goes to 0 of f of x plus h plus g of x plus h minus f of x plus g of x, all divided by h. And now we open the parentheses and reorganize the terms, and we have limit as h goes to 0 of f of x plus h minus f of x. So I am picking this term and this term together. I will kind of group them, and then plus, and now I am grouping g of x plus h minus g of x, and I would have here g of x plus h minus g of x. That is all divided by h. Now remember that if we have two terms in the numerator, we technically can separate them into two fractions, and we will have limit as h approaches 0 of f of x plus h minus f of x divided by h plus limit as h goes to 0 of g of x plus h minus g of x over h. And this is exactly the definition of a derivative of f of x. And this is going to be exactly the definition of derivative of g of x. So we can write it as f prime of x plus f plus g prime of x. And this gives us the sum rule. In fact, it can be extended to any finite number of functions, giving us the generalized sum rule, which is d dx of f1 of x plus f2 of x plus fn of x, that is equal to f prime 1 of x plus f prime 2 of x plus f prime n of x. And similarly, we can derive the difference formula the same way. Let's apply these rules to find the derivative of a polynomial. Find the polynomial of ddw of 2w cubed plus 9w squared minus 6w plus 4. Okay, so first we will separate each term into a separate function and take the derivative of each term separately. So we would have here 2 times, now what is the derivative of w cubed? It's going to be 3w squared, right? Because we're reducing the power by 1. Now plus, now we bring down 9, and then we take the derivative of w squared. So we take and bring this 2 to the coefficient times w, and now we reduce the power by 1. So 2 minus 1 is going to be 1. Minus, now 6, we just bring it down, and w, it's in the first power, so we bring down 1, and we reduce the power by 1, so we have w to the 0th power. And here, as we said, that the derivative of a constant is 0, so it's plus 0. So now let's simplify it. We have 6w squared plus 18w minus 6 times 1, and that's going to be minus 6. Okay, so this technique works for any polynomial. We simply apply the power rule to each term, multiply by the coefficient, and add the results.